Today, the Glen Canyon Dam opened to let water through to the Colorado River to help rebuild natural habitats. The high-flow experimental release sent about 42,000 cubic feet of water per second down the Colorado River today. This man-made creation mimicked natural flooding that occurred prior to the construction of the Glen Canyon Dam. Releasing water helps to move the built-up sediment out from behind the dam and bring it downstream. It also aids in building habitats for key fish and wildlife. It could also potentially reduce erosion and increase beaches along the Colorado River.
You know, the Colorado River would be naturally very muddy. It would be carrying sediment down, you know, historically, but the dams have stopped that and turned the water clear and cold. So now what we do is we wait till sediment comes in from the side canyons, piles up, and then by cranking open these valves, you push all of that sediment down the valley.
The last release in Glen Canyon was in 2008. The next one will be on an as-needed basis. The release did not affect Lake Powell's water levels.
So, interesting situation since, of course, you know that Lake Mead and the West is in a kind of state of drought right now. All right, so we have been talking for the last little while about accelerations. Actually, I have this little video for some other reason, but it might be worthwhile using it here. I guess I'll put the sound down. And so what we said we'd like to do is we'd like to be able to deal with conservation equations. So the conservation equations that we're interested in dealing with are for conservation of mass, volume in equals volume out, conservation of momentum, momentum into a container, momentum out, and also energy. So those are the three types of conservation that we'll deal with. The simplest by far is mass, primarily because mass, as opposed to momentum and energy, is a scalar rather than a vector, and it turns out to be easier. And we made the point before that when we're dealing with this, we have to say something about reference frames. And we spent some time talking about individual reference frames that allow us to be able to define behavior. We talked about the fireboat, squirting water ahead, and relative velocities. Talked about taking a fluid and moving it up in an elevator and being able to say something about magnitudes of rates of different viewpoints. And so the main outcome, I think, of that was that it makes a difference whether we're talking about the substantial derivative, which is something that's happening to something that's attached to the moving reference frame. So if it's, for instance, an acceleration, so in other words, if this was a velocity in the vertical direction that this is experiencing, then this pen, if you're attached to the pen, that would be the acceleration that you were experiencing. If you want to be able to compute that by not being attached to it, by being an observer from some distance away, you can do that by looking at the other components. Those would be how the velocity changes in time and also how the velocity changes in space. And so in our simplest way of dealing with this, we could write this expression basically as rate of change of velocity with time. And if we only have one component dealing with the vertical direction, then we're dealing with rate of change of velocity in space. So we're just multiplying dv dt by 1, dz over dz. This ends up being the velocity in the z direction by definition. And so this term that we're adding onto it is just velocity multiplied by the rate of change of velocity in space, this term here. And so it's kind of epitomized, actually. I only just thought about it coming over here. This little movie that I have is for a different reason. I guess I can have both of them on the page at the same time. Is that shows this quite nicely. I'm doing it for a different reason. I'm looking at using control volumes to be able to do a mass balance in this 16 or this 20-ounce beaker. But if you look at the jet that's coming out of here, this is something that we know, right? This is a, if I can get this is a free jet. It's coming out of the tap at some not very high pressure. If we stall it, if I can do that, I guess I can't do it with the pen. Let me just move it back. So you could imagine being attached to a bead of water and falling down with this. So if a bead of water falls, it's just falling exactly the same as my pen would be falling. But if you wanted to calculate what the accelerations were at any given point, you'd want to know what the velocity is at this point, the velocity is at this point, and if you know how those change, you could calculate from this. We also know that this term can also be written as, for instance, how can we write that? Something like the rate of change of v squared over dz to the half is the other way to do it. And so you should be able to use the equation for a free jet, which we know is the velocity is equal to 2gh square root. And you should be able to substitute it into here and into here. And you'd expect as a result of that, if this is an acceleration that you get, then it should be equal to gravity. So I'll let you do that and see if you can do that. But it's basically the same thing. The most important thing to come from what we talked about last time was that we can get, this is only experiencing a given acceleration. It doesn't matter whether we're attached to it or we're viewing it from another reference frame. The reality is that this is experiencing only one acceleration. So both of these expressions, from either being attached to it or being a dispassionate observer from some distance and being able to view things, should give us the same result. This term will be 0. And the reason that term will be 0, of course, is that if you look at this thing, the velocity here at time t0 is some number. If you come back in another day, it's still that same number. So change in velocity at that point is 0. So the only thing that's changing is the velocity here has to be accelerating as you go down here. You kind of know it's accelerating as well because you can apply continuity, right? So the other observation, which I think is interesting in this really very simple example, is if you look at the jet that comes out of the faucet, perhaps you can see it best as it just starts, is it comes out quite wide. So it comes out quite wide here. Cross-sectional area is large. Cross-sectional area here is small. And so the other thing I suppose we know from continuity, which we've also used, is that V1A1 is equal to V2A2. If A1 is large, then that means that the velocity here has to be smaller than the velocity here, just in ratios of those. So very straightforwardly. And so you could also, by looking at those cross-sectional areas or the widths of that jet, you could say something about the actual velocities just from continuity without using anything else. So that's diverging a little bit from what we've been doing so far, but that's it. Okay. So the important thing is frames of reference. In the elevator, holding the water, this is the acceleration the water experiences as you go up and down the elevator. Standing outside the elevator, watching the velocity of the elevator and the water, this gives you exactly the same acceleration applied to it. So they have to be exactly the same. So it turns out that we're also interested, let's think about doing a couple of things today. We'd like to be able to talk about taking these accelerations, which we've talked about in this different reference frame, and put them in a reference frame that's of interest to us. And that reference frame of interest to us is along a streamline. And then we'd like to be able to talk about formally balancing masses in and masses out. And we'll use what's called Reynolds transport theorem, which is a general statement that allows us to be able to balances of mass, momentum, and energy in our systems that we'll use for the next 2.5 weeks, including today, to be able to say something about those balances. So that's kind of where we're going with this. To be able to, so we'd like to be able to talk about, all our work in Bernoulli has been talking about flow along a streamline. And we've made the point that there are accelerations in this flow both along the streamline and also normal to the streamline. Actually, there should be accelerations, right? Not velocities. Accelerations normal to the streamline and also parallel to the streamline. And so we can calculate what the magnitude of the overall acceleration is if we want by looking at those individual components. And the easiest way for us to do that, well, we could go to this little derivation page here, but I think it's easier to be able to just go back to our definition of Bernoulli. So if I go back to, I think it's page 1, in this it's 132. If you recall our original statements, so we spent some time talking with these before. Remember that we have two statements for Bernoulli. One was a differential one, which is equal to 0 along a streamline. And one is the integrated form, which we've generally used. So we've generally used this second one and not the first. And likewise, normal to the streamline, we have a differential relationship and also the integrated one. The difference between one is equal to 0 and one's constant. So what we could do, and what I'd like to do, is take each of these, and instead of taking the normal Bernoulli that we use, I'm going to take the differential format of it. And I'm going to write them just out here a little, so just down here. So I'm going to write them out just in a normal form. So this is change in pressure with direction along the streamline. That's this term here. I'm going to write this part next because I can. Unit weight times change in elevation with distance along a streamline. And then this half rho change in velocity squared with direction along the streamline, just as a partial, is equal to 0. The reason I've written them that way is because that these are actually equal to, so if we draw a little dashed line down here, this is equal to force for both of these components minus mass times acceleration equals 0. And so this is, if you like, well, this is my notation for parallel to. This is parallel to a streamline. So we're just rearranging this equation to be able to look a little different. If we take the normal to the streamline one, then again, if we write those terms, I guess this is the first term, change in pressure with location normal to the streamline, plus this would be the next term, unit weight times change in location normal to the streamline. And then the convective acceleration term, which is rho v squared upon r, again is equal to 0. This is a plus, not a minus, because it's the way it's come out in all of this. If we look at what these expressions are, what are the units of this? And this is flow perpendicular to the streamline. So we have flow that looks like this. We have flow in the direction of the streamline. This is v. And we have a coordinate system. So this is in the streamline direction. This is the normal direction, as we talked about before. This has to have some curvature in it if this is going to be a term. And this is, these two separately are, this is convective acceleration, as we've talked about before, change in velocity to location, and this is centrifugal acceleration, swinging things around our head. What are the units of this? This is in the units of pressure, which is equal to force over area divided by length. So you can think about this as a force per volume. So each of these terms is a force per unit volume. And so really, it's not just force we're plotting, it's actually force per unit volume. So we're just dividing through both sides by volume. And so what we'd like to be able to do is be able to cancel out the magnitudes of this. So if we multiply, for instance, both sides by 1 over density, which we can do, right? 0 on the other side. So what is volume times density? Volume times density is mass, and so this crosses out with this. So by definition, the units of this, if we do the same thing, so this initially is in units of force over volume. I'm going to divide everything here by density. We don't care about the terms on the left-hand side. And this would change, and this is density. And so by definition, these terms here are accelerations. That's all I've done, so as simply as possible. And so what we can do with this is we could say that the acceleration that a particle sees is equal to its convective acceleration plus its centrifugal or centripetal. And if we do that, then these individual components are just, it's going to be convective acceleration is going to be a half change in velocity squared along the streamline, ds, multiplied by the vector, which is s. So this is a little vector, and this is also a vector. Nope, sorry. Yeah, no, that's right. S. Plus the centrifugal acceleration is just v squared over r multiplied by m. And so these are vectors which represent a direction, and these are just scalar magnitudes. So this is a scalar. In other words, it has a magnitude and not direction. And this identifies the direction which it's applied. And so in other words, what we could do is if we wanted to know what the acceleration is at a particular point, at this point here, we can get it from knowledge of the changes in velocity squared at that term, just from the same terms that we have in Bernoulli. And so for instance, if we wanted to know what the acceleration was of this particular geometry, then we need to know what the values of these vectors are. And so if this is 45 degrees, that's the easiest one, right? So what are the values of these vectors? S would be a vector like this. If this is, say, 45 degrees, then this unit vector is going to be equal to what? The easiest way to think about it, I suppose, is that if this is a unit vector, then this would be 1 by 1. If that's the case, then this would be 1 plus 1 squared. Sorry, 1 squared plus 1 squared, square root, which is equal to root 2. And so if you divide this unit length by this length, then it ends up being, if this is equal to 1, then this is equal to 1 over square root 2 and 1 over square root 2. So in other words, if this is this, then this term here would just be these components in the x direction. So we use our right-hand rule. So x, y, z is pointing out of the page at me, and it happens to be 0 in this case. So x would be this. This is y. And so this would be, let's take 1 over square root 2 out. This would be 1. This is positive y. This would be 1. And this would be 0. So this would be this term here. So in other words, if you know what the velocity is at this point, you certainly know what velocity squared is, and you need to know how it changes in space. And if you do that, then you know what this scalar is. If you multiply this scalar by the direction of this vector, you're able to get the acceleration in x, in y, and in z. Because obviously, not obviously, but clearly accelerations have 3 components. Likewise, what's the value of this vector here? This is going to be orthogonal to this. I can't draw it so well. This is going to be n. So it'll have the same lengths. So what will it be? The component in the x direction is going to be this, which is, again, 1 over square root 2. This x component is in the negative direction, so it's equal to -1. This y component is in the positive direction, so it's +1. And it's all in the xy plane, so the component in 0 is 0. And so the bottom line is that we can get, if we know what the velocities are and how they change in space, convective accelerations, a magnitude of the streamline acceleration, which is this convective acceleration, and also the magnitude of the centripetal acceleration. Of course, if the radius, r is the radius pointing in here, so r is this length to the point of curvature, so this is r. So if r is infinity, then this term is 0. Right? There is no centripetal acceleration if you're flowing in a straight line. But if it is going around a corner, then it has some effect that's due to that. So we can always calculate the accelerations due to that. And of course, there'll be 3 accelerations. This is actually a vector, because this is a vector, and this is a vector. And we're just adding those components together. So we calculate what the components of the convective acceleration are in x, y, and z, calculate what the components of the centrifugal acceleration are in x, y, and z, and then put them together to get that. And so we've skipped, we've done it that way to save doing it slightly differently. But if you feel that you want to go through a longer derivation, you can go through it. You end up with exactly the same result. This is exactly the same result we talked about before. It's kind of a long derivation. Here we've just written the convective acceleration. We've written it slightly differently as a half change in velocity squared ds. But of course you know this is exactly the same as that. Okay? So we've kind of done it heuristically by looking at what Bernoulli's equation components are and what these are. And so it's kind of a long derivation, but the end result is the same. And there are a couple of examples to be able to see if you understand exactly what's going on. It's kind of esoteric. So we can calculate the accelerations, so what? We don't really need them. So if you have equations for what the accelerations are, which of course you do in textbook examples, you can use them, but you don't often have those expressions. The one place you do have that expression is in the first thing we looked at, and that's for the behavior of a free jet. We know that the velocity of a free jet is square root 2gh, and so you can take that and substitute it into that expression, and you could get, in the case where it's just free falling, this is just the magnitude of the convective acceleration. If it's falling as a free jet, obviously it's falling straight down. The curvature of this is infinity, or the radius of curvature is infinite. Zero curvature, infinite radius of curvature, and therefore this term would be 0, and just as a result of that, you'd get AZ is equal to G, and you get AX and AY are both equal to 0, as it would turn out. Okay, so anyway, a little bit esoteric. But we've gone through it anyway. So one of the main reasons that we wanted to talk about frames of reference is so that we can look at behaviors for conserving quantities. And the first quantity that we'll conserve, maybe we can look at this again, is mass. And so if we're looking at conserving mass, we talked when we first discussed this last week, is that we can look at a few different reference frames. We can look at a static reference frame where you take a pipe and you allow water to flow through that pipe, and you do the inventory of how much goes in versus how much goes out as it goes across this pipe. You could look at the case of a jet engine where the pipe is moving and squirting fluid out of it, so it's not static anymore, it's not deforming in space. And we could look at the case where we have a balloon which is filling up with water and getting larger, or discharging air as we have it flit through the air. So those are the 3 cases: static and stationary, moving but not deforming, and deforming and maybe moving at the same time. So what we'd like is to be able to analyze the case where we can accommodate all 3 of those things together. And so we could apply those also in this particular case as well. I mean, this is a relatively simple geometry, but you can imagine being able to work with each of those control volumes. And we will do some examples dealing with that. So I'm going to stop it in a second as we start filling it up with water. And so what we could do is we could stop it there. So for instance, we could choose a control volume which is this box here, which has stuff going into it. And if that control volume is static, then we have to account for both the stuff that comes into it, but also the fact that this surface here is moving up through the control volume. So a static, non-deforming control volume would just be this box at the bottom of the glass, and stuff would be coming into it, and stuff would be going out of it. And we could do the mass balances based on that. We could also use a non-deforming but moving one by, for instance, making a box that attaches itself to this, and as the water keeps on flowing into here and getting higher and higher, then we could have that box not change in size but move up with this free surface. And that would be another moving but non-deforming control volume. Or we could do one, I guess we can't really do a deforming and moving one. Well, yeah, the easiest deforming one would just be to take one that completely encompasses all the fluid that's in here and grows with the fluid, and then it's both deforming and moving at the same time, because this upper surface is actually moving as well as deforming. And so we can deal with those in some kind of formalism, which is what we're seeking for. And so the formalism that we'll use is named for Osborne Reynolds. His name is Reynolds, not with an S, not there. And it looks kind of complicated, but it's really relatively straightforward if you write it in words. And what it says is that whatever the quantity is, and the quantity is going to be this intensive parameter B, quantity rate in minus out. So maybe it's easier if we think in terms of mass. So mass rate in minus out has to equal accumulation and this term in our cases is rate of change in larger system, which for us will typically be 0. And so accept that for now and make life a little easier. So I guess it's written down here. I guess I didn't notice that. So what we talked about when we talked about our simple conservation of mass equation, our simplest one was for this geometry, right? Between two streamlines, has a velocity 2, an area 2, a velocity 1, and an area 1. And we just wrote that V1A1 is equal to V2A2. Or I suppose we could write it better as V1A1 minus V2A2 is equal to, and I run out of space, is equal to 0. And so that's this term here. So we say in 10 minutes, 10 people go in, 9 people leave, we net accumulate 1 person. And so this has to just balance. So in words, it's really quite straightforward. It happens to have an integral in it that we might be concerned about, but we can explain that in some terms. So accept this as a general expression. Realize that it describes some quantity in it, this intensive quantity B, and an extensive quantity uppercase B, which are related to each other. And they're related to each other in this form. Lowercase b is just the extensive quantity per unit mass of the system, just divided by mass. And so the extensive quantities that we'll want to conserve are mass, momentum, and energy. And so that lays out our path for this week and the next 2 weeks. We'll talk first about conserving mass because it's a scalar, it's simple. And then we'll deal with momentum So momentum is really just another statement of Darcy's law. So you can take a fire hose, you can turn it on me, and we'd be able to calculate what the forces are that are applied on my chest by doing that, by doing something a bit more sophisticated than Bernoulli. Or we could do the Jetlev problem in something a bit more sophisticated in Bernoulli. But it's basically Bernoulli. The reason mass is easier is because you'll see that mass is just a scalar value. Momentum has a mass times a velocity. Velocity has x, y, and z, so it's a vectoral quantity. And likewise, energy, in terms of kinetic energy, is also a vectoral quantity. This intensive property is just the extensive property per unit mass. And so what we could do is we could put these values into this expression here, and this expression here, and all of a sudden we have a general equation which describes conservation of these three systems. And so we'll just do the first of those today. We'll save the other fun for later. So we won't do this or this, but we'll do that a little later. Okay? So, physically, what does it mean? So let's again talk about this in terms of physical description of what's going on. Well, if we kind of dissect what does an integral mean? An integral you could also write as a summation, right? So for instance, if we're going to substitute for, so in other words, in our particular case, B is equal to mass over mass. So in other words, B here is just going to be 1. And the value of B here is just going to be equal to mass. But we've said we're going to assume that the change of that in time is 0, and so that falls away. So this term is still 0. So what do these quantities represent? Well, what's the easiest way of looking at it? Let's say the density. This is density of the fluid that's in our control volume. So people in mechanics always like to draw control volumes as some fancy kidney shape. So we have some shape that we apply to this. And that has some volume, as we've used. So if density is constant, we could take this outside the integral. And so we could write this property as the rate of change in time of density multiplied by the integral of 1 dV over the volume. So this term here, by definition, is just the volume, the total volume here. And so this term, if you like, is just rate of change with time of density and volume. So it's no longer an integral, it's a differential, but it's a bit simpler and easier to deal with. So that's one key component that we have that describes this behavior. And that's this. So we've taken this term and we've replaced it in some kind of words to be able to say what's going on. I guess it's actually this whole thing here. What about this? Well, this looks a bit more scary, but really it's not. What are the individual components of this? What this is doing is it's taking, I guess if we write it down here, so yeah, I guess it's written down here. So if we write this exact term here, we know that this is 1, so that doesn't affect it. So this is saying density multiplied by a velocity times a normal vector. And so physically, what does that mean? Well, this is the normal to the boundary vector here. And the flow out of this system could be at any random direction it chooses. But what we'd like to be able to do is we'd like to be able to take the flow out of the system, which is occurring in this direction here, and relate it to one single unique property. And that single unique property is the flow that's coming out normal to this boundary. And so this dot product here, which you certainly would remember from your past, is just the component of the vector of the flow that's normal to this boundary. That's all this says. This is just normal to flow, normal to this boundary. So it's a single property. It's not a flow in the x direction and a flow in the y direction. Instead of having vectoral quantities, we convert a vectoral quantity of a velocity in x, y, and z, multiply it by a vector, and that dot product gives us a single magnitude, which is the flow normal to the boundary, a scalar magnitude. So we have a flow velocity out of the system multiplied by density. So a flow velocity multiplied by a density integrated over an area starts all of a sudden to look like something you've seen before. Right? And so this, if you multiply each component, so this statement here is a slightly less scary view of this, right? So in other words, we've taken our continuity relationship, we've multiplied both sides by density because we conserve mass, not volume, because mass is the invariant extensive property we'd like to deal with. Extensive property, rather. And this is our expression. And so this is just one way of writing that. And so this is also, we could write this, and we will choose to write this. This is a mass rate of flow. So a velocity times an area is what? Meters squared per second times, meters per second times meters squared is, this is meters cubed per second. This is kilograms per meter cubed. And so by definition, units of this are kilograms per second. So we can write this in terms of mass rate. Yes?
I'm sorry, can you go back to the first step and explain how you got E equals I over M? That's equal to
This one here?
Yes.
So all we're doing, so we're not going to derive Reynolds transport equation, but we're going to realize that each of these quantities represent the things that we're conserving. And so by definition, this extensive property B can take any of these forms. It can be mass, it can be mass times velocity, it can be a half mass times velocity squared, any of those. And by definition, this intensive property is just this term divided by whatever per unit mass. And so in this particular case, it's going to be, this is going to be mass divided by mass, which is just 1, which goes here. When we conserve momentum, it's going to be mass times velocity divided by mass. And so we're going to be left with B is equal to velocity. That's all. So you just have to take it on trust as a definition. So you need to know what this kind of means, and you need to be maybe comfortable thinking about it. But ultimately, you'll probably choose to use it in this form, with these two components. So if you put these two components, as we'll go somewhere here, I guess this is this derivation here. So let me write it in the way in which you'll ultimately use it. So it's quite important. And it's a very simple rubric, if you like. So conservation of mass. So we're using Reynolds transport theory. And we're going to do it on a block. It looks like this. Much easier to think about than the regular kidney-shaped thing. So we have V1, V2, volume of this. So that's our geometry. We're going to make this a no-flow boundary. We have the faces aligned relative to the x and the y coordinate system. It is a right-handed coordinate system, right? With z would be pointing towards me. And so if we write out Reynolds transport theorem in our form that we just defined, it is rate of change with time of, what was it? Is it, you have it here, right? So all I'm going to do is going to take it from here, of this, and this. So those are the two quantities I'm taking, nothing more than that. So rate of change with time of density times volume plus mass rate equals 0. Mass rate of change. So in other words, dm dt is this shorthand. You must have seen it, right? The over dot is just mass rate. They're exactly the same as each other. And so what do these two terms say? So we can take this and we can divide it up, and we can differentiate in parts this. So we can take this and take it as density times the rate of change of volume of our control volume with time, plus volume multiplied by rate of change of density with time, plus mass rate of change equals 0. And so what happens in this case? So this is a pipe, I suppose, so it's not deforming, it's not moving. What's the rate of change of the volume of this control volume with time? Solid pipe, certainly there's fluid going into it and out of it, but the volume of the control volume is not changing. 0. If the density of the fluid going in and the density of the fluid going out are equal, let's make life easy for ourselves. Density isn't changing in time either. So, what's this? So now all we have to do is be able to do this accounting. So remember now, bless you, that mass rate of change is equal to a density times a normal to the boundary velocity multiplied by an area, which is our way of writing it. And so the reason we have to state it that way is because this normal to the boundary velocity is relative to this vector here. So this is our normal vector. And so the easiest one to do is the downstream one. So what's m dot 2? We'll do m dot 1 and we'll do m dot 2. m dot 2 is what? It's equal to the density of fluid going out. It's equal to the normal to the boundary velocity, which is aligned with this normal. So it's equal to plus v2. And it's multiplied by the area. And if we just do that, if the velocity is uniform on the surface, then this is this expression. Okay? So that's the easier one. The mass rate going in is kind of similar. We have a density going in, so I guess this is also 2, right? Density going in. What's the velocity? Well, the velocity is relative to the boundary. This is the normal to the boundary here. So the dot product of these, if you have a velocity going in this direction, I guess things are backwards for me. So if you have I'm going to do it on this. If you have the velocity going into the material, going across this boundary, the normal to the boundary vector is this, so they're oppositely aligned. You take the dot product of two things in the opposite direction, you can do the calculation, it's just minus 1. And so this velocity here has to be minus v1. And then the area is just a1. And so if you put this all together, we end up with 0 from this term, plus 0 from this term. I'll put m1 first, which is no, I'll put M2 first. Rho 2 V2 A2 minus rho 1 V1 A1 equals 0. And so it's actually no different from everything we've done before. It's just a formalism that allows us to deal with things in a little different way. And so that's worthwhile understanding. So the key thing here, I think, what are the key things? One is that we can take the accumulation term, which is this term, and we can look at it as a change in volume of the control volume for constant density, or a change in density in the control volume for constant volume. So that's really what these are. And we have to equate this accumulation term, this is the accumulation term, with how much goes in versus how much goes out. The rule of thumb for this is that if mass rate is in, then it's negative. This is mass rate in. This is the dot product, which is going in here. It's opposite to this, and therefore it's negative. If the mass rate is out, it's the opposite. Positive VE. Someone went through a whole class saying, what does this plus VE mean? Positive. Negative. Just my shorthand. And so that's the sign convention you need to remember to be able to have this work out. And I guess the other thing you need to know is that these would be positive. So if volume is increasing, it's positive. And if density is increasing, then it's also positive. So I guess those are the two aspects of the sign convention that you need to know to be able to avoid using Reynolds transport theorem, but use it in this form here, which includes, as I say, in the simplest way, if you break it down into just language of what it means, mass in minus mass out, or actually it's actually mass out minus mass in if you think about it. We should say it that way. And relative accumulation. Accumulation in two ways. Either accumulation by pushing air into a closed container where the density of the air will increase but the volume of the container won't, or by pushing fluid into a tank where the density of the fluid doesn't change but the tank's volume will change because the surface rises. So both of those are accommodated for when we split this term into its two components. Okay? Yeah, sorry. This box in the lower left? I mean that if your volume is increasing, if you're going from 1 meter to 2 meters in volume, then that is a positive volume change. So the sign convention for volume change is increasing volume is positive, increasing density is positive, and mass rate out is positive, and mass rate in is negative. That's the sign convention. We're not going to get to it, I don't think, but there's a couple of simple examples kind of showing this. Basically, those two conditions that we met. And so if you feel as if you want to, think about what dot products mean. This is really the definition of a dot product. It gives you the component of a velocity vector in the direction of the normal to the boundary. So this is the boundary of our system that it's going beyond. And this just explains exactly what we've done. And with two very simple examples. One where you're pushing a gas into a closed container and looking at how, in this case, presumably if it's constant volume, the density must go up and not be 0, whereas the volume change with time, this would be 0. And therefore, the mass in minus the mass out, which of course if you shut this valve off, this would just be the mass in. And therefore, by definition, the mass in would have to equate with the change in density multiplied by the volume of the system. So in other words, the amount of mass going into the system has to always equal to the accumulation of the system, because that's the only place it can go, because this term is 0. You can do the same calculation just here. So maybe look at these examples just to solidify these in your mind. Important concepts. Transport theorem is a generalization to be able to look at any mass balance equation any energy balance equation or quantity equation, we've chosen it for mass balance. It looks kind of complicated, but it really breaks down to two components: how much in versus how much out versus accumulation. If you quantify each of those terms as we've done, then the expression always looks like this, and you can always solve for it if you keep hold of the sign convention, which are density changes are positive if they increase, volume changes are positive if they increase, and mass out is positive, and mass rate in is negative. Maybe backwards from what you think. Okay? All right, and leave it there. Thank you.